Hello, my name is Tekamul Buber. I'm a senior principal engineer at Maury Microwave. And today, I'm going to present you our paper titled Measurement Uncertainty Analysis and Power Amplifier Design with Uncertainty Added as Parameters. Our presentation consists of 4 topics. First, we are going to talk about S parameters and why uncertainty is needed in measuring S parameters. Then I'm going to talk about traditional and enhanced VNA measurement models. Then I will give an example for a measurement and design with uncertainty information. And finally, we will have a conclusion discussing our results. First, the motivation, why we need uncertainty with the S parameter measurements. As RF and microwave engineers know, S parameters or scattering parameters is one of the linear network parameters for microwave circuit, component, and system design and analysis. Vector network analyzers or VNAs are used to measure S parameters, and they need to be calibrated. Basic measurement data provided by the VNA are estimated S parameter values, as is the case with every measurement. To understand the need for uncertainties in S parameter measurements, let us imagine the following situation. Let's assume that an engineer has to design a power amplifier, PA, with at least 12 dB gain, or S21, over the frequency band from 10 GHz to 42 GHz. The designer designs and prototypes and then calibrates the VNA and measures the S parameters and happily sees that the PA meets the gain spec, S21 spec, over the entire frequency band. It's better than 12 dB. So the designer is happy, reports the result to his supervisor, and then after some time, maybe an hour later, the supervisor or the manager comes, and when the engineer shows the result, he suddenly sees that the amplifier is actually not meeting the gain spec anymore after an hour or after some period of time, especially at the end close to 40 gigahertz range. The red graph is now shown on the VNA. Why did this happen? An hour earlier, when the engineer looked, he saw the black plot and it was meeting the spec. Now after an hour, the plot changed, it went down, and it's not meeting the spec. The main reason why the measurement result changed over a period of time is because every measurement has actual uncertainties, random uncertainties, and sometimes even systematic errors that have not been accounted for lead to these errors. And the type of hardware selected for the measurement and how it is handled by the end user during the measurement is the main cause of variation in the measurements. And we can define 5 main contributions for S parameter measurements. First, VNA drifts. Second, there is a noise in the VNA, and there are some non-linear effects in the VNA. Second, the cables used in the measurement, they have some stability issues, and the cables are moved usually during the measurement, and calibration as well when we connect different calibration standards or DUT. Third, there are connector repeatability issues. Every time we connect and disconnect a connector, we won't be able to connect it exactly the same way as before. Fourth, the CalKit definitions, the characterizations of the Cal standards used during the calibration might themselves have uncertainties because they are based on measurements as well, and every measurement has uncertainties. And fifth is the operator skill. How the operator who is performing the measurement does the measurement setup, how well he installed everything, and how well he handles the measurements. As we mentioned, every measurement is actually an estimate of the actual value, and we don't know what that value is. And the estimate we get from our measurement has uncertainties, meaning the actual value could vary within some plus or minus range around the estimated measured data. And the uncertainties are contributed, as mentioned before, by the VNA, cable, CalKit, operator, and connectors. After talking about the need for uncertainties in S-parameter measurements, let us now talk about the VNA measurement models, the traditional and the enhanced measurement models. The traditional VNA measurement model is a very simple one. It consists of an error box or error coefficients cascaded with the S parameters of the DUT or the Cal standards. The DUT and the Cal standards are connected to the reference plane denoted by 2, and raw measurements, raw data are acquired by the VNA inside the VNA in the receivers. In this model, systematic errors are only partially considered. No random errors are accounted for, as well as some systematic errors are also unaccounted for, such as cable, CalKit uncertainties, connector repeatability, VNA noise, drift, nonlinearity. All these are unaccounted for. The calculated error coefficients during the calibration have themselves also uncertainties because they are based on measurements, and any measurement has inherently uncertainties, and any quantity calculated from these measurements will also have uncertainties. These uncertainties are not accounted for during the calibration process in the traditional measurement model. However, these uncertainties can be estimated, some of them at least, with some post-calibration measurements, and we call these the residual errors. The problem with these residual error estimates is that very simplistic models are used, and the so estimated residual errors can be sometimes over or sometimes underestimated. One of the very well-known techniques to estimate the source match, residual source match, is to connect an airline terminated with a high reflect standard or device and measure the ripple peak to peak, the ripple seen in the reflection measurement, and estimate the residual source match from the peak to peak ripple measurement. There is also a similar method for measuring or estimating the residual directivity. The enhanced VNA measurement model has some additional blocks as shown in the diagram, such as the box R and D to account for VNA noise, nonlinearity, and drift, and the box C to account for cable stability, connector repeatability, and operator skills. And the box S includes the uncertainties of the calibration standard characterization. The new model not only enables to estimate the traditional error terms accurately without significantly over or underestimating, but it also estimates the individual uncertainty contributions due to cable, VNA drift, nonlinearity, connector repeatability, and calculate characterization imperfections. These contributions are then propagated to the final DUT measurement and its S parameters. Let us look now at an example with an amplifier design and measurement. To give an example, for the measurement and design of an amplifier, we need to first characterize our measurement setup and the equipment, such as VNA, cables, adapters, and then measure the S parameters of the transistor with uncertainties and de-embed the fixture of the measurement, and then design the input and output matching networks for the amplifier, and then finally cascade the matching network S parameters together with the transistor S parameters. And all this cascading with uncertainties can be done in software tools such as VNA tools from Metas or Insight software from Maury Microwave. In our particular design example, when we measured the S parameters of the transistor and looked at the uncertainty budget, we noticed that most of the uncertainties are coming from the cable stability and the cal standards uncertainties. The analysis of such budget is done using again software tools such as VNA tools or Maury's Insight software. And the benefit of this budget analysis is once we know where the largest uncertainties in our measurement are coming, we can try to reduce them accordingly. In our specific example, we measured a gas transistor at 2.4 GHz with uncertainties, designed input and output matching networks with ideal components, and then cascaded the matching networks with the transistor using the mentioned software to obtain the overall S parameters of the amplifier. This way, we could see how the uncertainties of the initial transistor measurement are propagated to the uncertainties of the final amplifier design, including the transistor and the matching networks. For example, in our case, the magnitude of S11 for 95% confidence interval for the transistor was plus or minus 0.07 dB, which increased for the amplifier to plus or minus 6.4 dB. To conclude our presentation, we showed the necessity and need for uncertainties in S parameter measurements, and we showed that it's feasible with modern software and hardware tools to estimate the uncertainties of the measurement setup and propagate them to the final S parameter measurements and use that in the design of a power amplifier and see the total uncertainties in the final amplifier design. By using the uncertainties of the S parameters, one has more control on the measurements, one can verify and validate a calibration of a measurement system. By knowing the uncertainties, one can estimate the worst and best cases in the model and designs and select the suitable circuit topology and components to reduce the fabrication variation. To improve the final product, one can revise the test criteria and improve the performance of the lab's measurement facilities, redefine the fail and pass conditions based on the measurement uncertainties, and provide more information and data to the end user or the customer.